Hi, I'm Mrs. Burns, and welcome to the first lecture of our Chapter 5 section. And today we will be talking about acids and bases. You can find this in 5.1 of your BC Science 10 textbook, and it is kind of a big section, so we are going to look at this for 2 days in class. So, what are these things, acids and bases? Well, they're just types of compounds that are structured in a specific way that allows us to classify or name them according to their properties as an acid or a base. So this chemist, Svante Arrhenius, found that when he put molecules in water, that they would break down, those molecules would dissociate, and they would do so differently. So here we have 3 vials and pretend that they are in water. So in the first one, if he found that there were lots of hydrogen, H+, molecules and only some hydroxide, OH molecules, then he noticed that there were more hydrogen than hydroxide. Sometimes he found that there were the same number of hydrogen and hydroxide. So let's put 3 of each here. So as you can see, the hydrogens are positive ions and the hydroxides are negative ions. And so in this case, the number of hydrogens and hydroxides were equal. And in other cases, he found that there were the majority of the molecules becoming hydroxide ions and only a couple hydrogen ions. So here he saw that there were more hydroxides. So these chompy guys, they just like to eat the one that is the bigger value. So he called these specific names. When there were more hydrogens, he called this an acid. When there were more hydroxides, he called this a base. And when there were even amounts of hydrogen and hydroxides, he called this neutral. So as you can see up here in figure 5.10, we have a scale of different ion amounts. So in this red area, the majority of the ions are hydrogen ions. And when there are all hydrogens or mostly hydrogens, we have an acidic solution. When you have all hydroxides or mostly hydroxides, you have a basic, or what sometimes they call an alkaline solution. So basic and alkaline are just different words of the same thing. When you have equal amounts right here, only in the center is your solution neutral. Now you might have been noticing that I've been saying solution a lot. So we're always dissolving our items in water. So some sort of substance dissolved in water making an aqueous solution. We'll get into that a little bit more in a bit. So acids and bases solutions mixed together can neutralize each other then. This is very interesting. So if you have one hydrogen ion and one hydroxide ion, they're going to come together and make water. As you'll notice, this is balanced. So one thing, however, though, is that the arrow, you can change this arrow. It can actually go back and forth. It can go hydrogen and hydroxide make water, or water can become hydrogen and hydroxide. Now this is really cool. So if you have, say, lots of hydrochloric acid in your stomach lining and it is burning your stomach and you have a stomach ache because of it, you can take something like Tums, which are those little pills that are made of calcium carbonate, and that can neutralize the acid in your stomach and cause your pain to go away. So the hydrogens, the extra hydrogens, get paired up with a bunch of the hydroxides that you eat in your tablet, and those create water. So if you have lots and lots and lots of acid, then what you can do is add a base to that, and then these guys will make a water molecule. So in this way, you're neutralizing, you're evening out the different ions. That's really cool. So just how far acidic or basic are we talking? What is the scale here? Because some things like a lemon will really taste acidic, but other things like, I don't know, tomato juice doesn't taste that harsh in your mouth. So there are common differences here along this thing called the pH scale. And this is just how we determine how far along something is, how acidic it is. If it's 0, it's very acidic. If it's 14, it's very basic. And if it's 7, it is neutral. So here we go. Any solution with a pH of 7 is neutral, less than 7 is acidic, and more than 7 is basic. So I'm talking here 0 to 6.9 and 7.1 to 14. So as you can see, there are lots and lots of items that you probably recognize. Something like milk is slightly acidic. Pure water is right in the middle, neutral. Eggs a little bit basic. Bleach is basic. Soap is basic. Tomatoes are acidic. Lemon is acidic. If you have or if you know somebody that has acid reflux, then they're told not to eat as many acidic things because their stomach might let the acid up into their esophagus. So each number along that pH scale, these 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, indicates a 10 times change. So from 4 to 5 here, that's not just 1, that is a 10 times change. Well, let's write that in. But if you go from 4 to 6, we've got a 10 times and another 10 times. So you have 100 times change because you have a 10 times change and times another 10 times change. That's the same as saying 10 to the power of 2, and that's 100 times different. So if you have a pH at 9 and it drops down to 5, what was the increase of acidity? How acidic is it now? How many times greater? Well, we're going 10 times 10 times 10 times 10. So 10 to the 4, because 4 times, equals 10,000 times more acidic now that it's at a pH of 5. That's crazy. That's a lot. That's really interesting, actually, when it comes to ocean. The different coral and living creatures in the ocean need it to be a specific pH. That's why it has calcium carbonate all over the coral to balance out the acid in the water. So if there were to be something like an oil spill around here, then that would cause the water to be a little bit more acidic, which we see from here, just 1 point difference is actually 10 times difference. So little changes, what we think are just one number, are actually really, really huge changes and can offset the proper functioning of many living things. So then, what happens if you've got a beaker of clear liquid and you don't know if it's an acid or a base? You can use a pH indicator. There are many kinds of indicators. There are indicators that you can buy in a lab, or there are indicators that you can use at home. Something even in your kitchen like cabbage or something like that. So a pH indicator will change its color based on the solution that you put it into. So if you use something like litmus paper, you can see it in our figure 5.6 down here. If you use litmus paper, it will turn red if you put it into an acidic solution, for example, lemon juice, and it will turn blue if you stick it into oven cleaner, for example, which is a basic solution. So let's pretend that you put it into an unknown solution and it turns blue. Well, that's a huge range here between this neutral and basic. You know it's basic, but is it basic like an 8 on the scale, or is it basic like 13? So you can use another indicator to narrow down your results. So in this case, we'd probably want to use something like phenolphthalein or indigo carmine. So say we used phenolphthalein and it turned pink, then we know that our substance is higher on the basicity scale. And if it turned pink, maybe we even want to do then indigo carmine and see, did it turn yellow or not? Let's say it turned blue, or it stayed blue, then we know that it's probably got a pH around 9 or 10. So we can use these indicators to see if our solution is acidic or basic, and we're going to try that in class. It'll be fun. Okay, so we've talked a lot about naming things. So how would you name an acid or how would you name a base? Well, an acid is a solution we already know that has more hydrogens and hydroxide ions. And so you'll see this in the name, hydro. See the H at the beginning? But sometimes the H goes at the end. But this is only if there's a carbon in that compound. So if there's a carbon, like in this case, the carbon gets to go first and your H will actually go last. So your H will usually be first, but if there's a carbon, it'll go last. It's never really in the middle. Now also notice that we have here this word aqueous beside, because when we talked at the beginning, these are dissolved in water. So these are little buckets of water there. They're dissolved in water. That's how we know. So if you have HCl, usually that's hydrogen chloride. But if you have HCl dissolved in water, it becomes something else. It becomes an acid and we name it differently. So if hydrogen chloride is dissolved in water, which makes it aqueous, then we have to consider two things. One, hydro is written first. So not hydrogen chloride, now it's hydro. And I said before the root word. The root word here is chlor because we end instead with ic acid. So how are we going to write this? HCl is hydrochloric acid. So the hydro at the beginning, the ic acid at the end, and this chlor, this is our root word. This is the part that doesn't change. So hydrogen chloride is how you would write it if that substance was just by itself. As soon as you put that substance in water, it's an aqueous solution and you must call it its acidic name of hydrochloric acid. So don't get mixed up. It's really tricky. So sometimes your acids will contain oxygen. And in that case, you don't put hydro in the beginning. Don't add the hydrogen to those names. So if your name has an 8 with it, so chlorate, then you're going to add the ic acid when it turns into an acid. So let's take hydrogen perchlorate. See that 8 there? Now if we put this in water and it becomes aqueous, then we're going to just call it no hydro. Remember, you don't add the hydro, so what are you going to call it? Perchlor. That's the root word, perchlor. And now instead of the 8, we change that to an ic acid. So the perchlor here is the root word. The 8 gets changed to ic acid. Now if you have an ite, for example, hydrogen chlorite, then you're going to change that ite instead to us acid. Now hydrogen chlorite, you do not add the hydro, so you just put the root part first, chlor. Now instead of ite, you're going to put chlorus acid. So this is the new part here, the us acid. The chlor part is the root word. Don't keep the hydrogen if there's oxygen in your acid. So that's tricky, so let's try a couple. We already just did perchlorate, so let's do hydrogen chlorate. The chlorate we see is going to turn into an ic acid. And does this have oxygen or not? Yes, it has O2. So we are going to follow the rules here in number 2. This drops the hydro part, and we just get chlor. The 8 becomes ic acid. And if we were to write that formula, that would be HClO3 little l aqueous solution. Sulfuric acid, well, that's already an acid, so already named correctly. Woohoo! So let's just make the formula. We can look that up. It's pretty common. H2SO4, aqueous. An acid or a base is always aqueous. Hydrogen hypochlorite. Does this have oxygen in it? Yes, it does. Has O2. So we are going to drop the hydrogen, but because this part is the root word, we're going to keep that hypo part. Hypochlor. The ite changes to us, chlorous acid. And if we were to write the formula for that, it is HClO in the aqueous form. All right, on to bases. They're a little bit easier, not as many rules. A base is a solution where we already know there are more hydroxide than there are hydrogen ions. OH minus is usually written on the right side of the formula. OH minus stands for hydroxide. So, calcium hydroxide. Same thing when we were naming before in chapter 4. I like to write out the two ions and then check out what the charges are. Hydroxide has a 1 negative charge, but calcium is a 2 plus. So these are going to switcheroony down to the subscripts. So CaOH 2. Now I put the brackets around the OH because the 2 must apply to this whole thing, the O and the H. All right, ammonium hydroxide, ammonium NH4 plus, hydroxide OH minus, both of them are 1, switcheroo the ones, NH4OH. Beautiful. There is a great summary in your textbook on page 229, table 5.6, that really breaks down all of the comparisons that we just walked through. We will have a chance to play around in the lab. We'll have a chance to read our books and to practice these names more in class over the next couple of days.